Or is this something you sort of vaguely remember from the last chemistry class you took?
I kind of remember some of this stuff, but I'm still just lost on the vectors.
Oh, the
Like,
vectors. Oh, yeah. Yeah. It's a little tricky thinking because, again, like I said this morning, I have trouble seeing in 3 dimensions of my head, and you kind of have to be able to do that. So if you have two arrows and they're pointing exactly in opposite directions, then when you add them together, they sum out. They basically annihilate each other because one is pointing exactly in this direction, the other's pointing exactly in the other direction. They're exactly the same size, and so when you add them together, you get nothing. But even if they're pointing just slightly to the same direction, then they add, and the more the more they point in the same direction, the greater the addition. So if they point together just slightly, that would be a small net polarity, a dipole, a net dipole for the molecule. But the more and more they sort of point in the same direction, the bigger that addition comes. So just
so
think of it that way.
so that vector, as of right now for our class, we don't have to assign a number to how big the I guess the vector is. We're
Just
kind
just
of.
take the difference in the electronegativities. That'll give you an idea of how big it is.
Oh, okay, okay,
Yeah. So if it's a difference between like carbon and hydrogen, that'd be like a difference of around zero point 0.4. That'd be very small. But if it's a difference between, say, the hydrogen and fluorine, that's a much bigger difference. So that the bond dipole will be much bigger.
And the way that bond dipole is actually facing matters on, like, I guess the other dipoles.
Yeah, exactly. Yeah, they all do. The directions of them matter a lot because if, like I said, if they're all totally symmetric, like if
Yeah.
they're all pointing at each other in the same direction or all pointing away from each other in the same direction, then they just zero out. Because when you add them all together, you get zero.
Okay.
Yeah, so if you had two pointing up and two pointing down at exactly the same angles, when you added them all together, you'd get zero.
Okay.
Or if you had one small dipole pointing in this direction and a big dipole pointing in the other direction, well, the net dipole will be in this direction because one is just bigger than the other.
Okay.
But when you have something that's completely symmetrical, all those bond dipoles are going to be identical because they're all symmetric. They're all the same. They're all the same atoms. So then we don't have to worry about how big they are, just what directions they are.
Okay.
Like the one we worked on this morning, the SCO. Since sulfur and carbon basically have the same electronegativity, there's no dipole there. But carbon and oxygen, that's a big difference. And so when you add something that's very, very small to something that's very, very big, the very, very big one is going to take it. And so then the net dipole for the whole molecule is just going to look like the larger dipole between carbon and oxygen. Yeah, there's a lot to take in there.
Yeah, and when we have like a big molecule, like the one that you said we were gonna have, you were gonna give like a big tricky molecule and tell us like to fill in the bonds. When we have a giant molecule like that, how do we figure out which way the dipole's facing? We just kind of add them all up.
Using good old Vesper, figuring out who's in the middle,
Okay.
how many electron groups are around it, what shape is it, and then you put the atoms in the right shape. Then put the bond dipoles pointing at the more electronegative atoms, and then figure out, okay, which way are most of them pointing. And if most of them are pointing up, then you're going to have a polar molecule with the net dipole pointing up.
Okay.
Yeah, we can do some more. We can do some more examples of that.
Okay, I'm just concerned that coming across something on the test that it will one be kind of confusing to find the middle, and I was just wondering,
Oh,
can
I'll
we?
point it out.
Okay.
Yeah, if it's a big molecule, I'll underline
Oh,
the one you should put in the middle. Yeah, because if there's like 15 atoms there,
yeah.
yeah, who knows what the hell? There's probably going to be more than one middle, right? And it's like, yikes.
Yeah. Yeah. Okay. All right.
So in
Thank you.
that situation, I will, underline one of the atoms and say this one goes in the middle, or basically give you a clue as to this group goes on one side, this group goes on the other side, and this atom goes in the middle.
Okay.
Something like the acetone we had this morning. The carbon double bonded to the oxygen, that goes in the middle. So I like make it obvious which one goes in the middle. Yeah, because if I don't, especially with organic chemistry, if I give you a whole bunch of carbons, oxygens, and hydrogens, there's millions of ways you could put those things together. There'd be no way to know what they are unless I gave you a hint or showed you the outline. Because there's millions of different molecules that all have exactly the same formula with carbon and hydrogen and oxygen. Those are like super plentiful.
Okay. Thank you.
There's lots of different ones. Yeah, I'm a mean guy. I'm not quite that mean, I hope. Okay, well, we got 13 people. Might as well get started. So if there's any other questions, I was just going to basically start where we left off this morning and just sort of give you an idea of what the hybridization means, answer some questions about it, and then we'll just jump into the recitation. Okay. Does that sound all right to everyone? I'm checking the chat. Nothing in the chat yet.
Yeah, that sounds good.
Okay, there we go. So we just started looking at the differences between atomic orbitals that we're all familiar with by now, hopefully, S, P, D, and F, and what happens when two atoms love each other very much and form a molecule. There has to be some change take place. And I sort of introduced that idea with methane. And we're going to do some more of these this afternoon. But very briefly, I just want to point out what basically the main problem is. When we look at carbon and we see that it's 4 valence electrons are in the 2s and the 2p, we remember that 2s has a lower energy than 2p, right? As we fill up the different orbitals, we start with 1s, then we go to 2s, then we go to 2p, then we go to 3s. And each one has a slightly higher energy than the last. So if we're looking at carbon all by its lonesome, it has 2 in the 2s, and it has 2 in 2p. Yes, Ferris.
What do we just ignore the 1s orbital, or?
Yeah, because those aren't valence electrons. We're just talking about valence electrons right now. Yeah, so the 1s isn't involved in bonding. So we don't really deal with them here. Yeah, these are only valence electrons. It's a great question. That's why we don't really deal with those. We're just dealing with the bonding electrons. So what we have here are 2 electrons with lower energy and 2 electrons with a higher energy. But when we form methane, we have 4 bonds, and they're all identical. They're the same length. They have the same angle. They're the same in every way. Well, that can't be, because we should have 2 bonds with a higher energy and 2 bonds with a lower energy, but we don't. We don't see that. They're all identical. And the other problem that I sort of mentioned this morning was that we remember what the orientation of these, what the p orbitals were. Remember, they sort of go like this, up and down, side to side, in and out. And all the angles in between them are 90 degrees. So if these two p electrons from carbon are involved in bonding, we would expect those bonds to be 90 degrees from each other, because that's where the electrons are, right? But they're not. They're not 90 degrees. They're 109.5 in a perfect, four-sided tetrahedral shape. They're exactly the same. That doesn't work either. So there's a problem with the energy, and there's a problem with the orientation. And so sort of, so many years ago, chemists came to the conclusion that you can't have it both ways. You can't have these particular atomic orbitals to be solely responsible for the shape of the molecule, because it doesn't work. So what are we going to do? And so this is how we're going to deal with it. We form what are called hybrid orbitals, where they mix together. And so the number of hybrid orbitals that we need is going to equal the number of atomic orbitals that we mix together. So if we need 4 orbitals, what we'll do is we'll take 1s and 3p orbitals and mix them together. If we need 3 places for bonding, or 3 areas of electrons, we would take 1s and 2p's and put those together. And now the shape and the orientation of these new hybrid orbitals will maximize overlap. That was another thing we talked about this morning, that the overlap between an S and a P isn't as good as the overlap between 2 P's, because the 2p orbitals have the same shape. They have the same long shape. So if I overlap 2 long orbitals together, there's a lot of overlap in between them. But if I have 2 orbitals of different shapes trying to overlap, they don't share as much space. And so you don't get as strong a bond. So let's have a look and see what we're talking about here. So here we have beryllium chloride. Now, anyone remember how many valence electrons beryllium has? Have a quick look and see which group it's in. What group is beryllium in? Have a look at your periodic table.
7. Oh,
Not
sorry.
beryllium. Beryllium's a metal.
2.
2, right? It's in 2. So it has 2 valence electrons. So it is, and it has 2s, 1s, 2s. That's it. So 1s, 1, 2, 2s, 1, 2. But when we look at beryllium chloride, we get this shape. It's linear. We have beryllium in the middle. We have chlorine over here and chlorine over here. And it's a linear molecule. That doesn't make any sense, because the 2 bonding electrons of beryllium are in S. S is spherical. It's not linear. And so what happens? So the way chemists came to sort of understand how this works is it takes these 2s orbitals that beryllium has, that's where both of its electrons are, and it has empty 2p orbitals. So what happens is that you blend the s and the p together to make what's called an sp orbital. Now, an sp orbital kind of looks like an s orbital a little bit, kind of looks like a p orbital a little bit. You see one side of it kind of looks s-like, the sort of, the big fuzzy side kind of looks like the s part. And this one here kind of looks like the p part. They're mixed together. And so this is what two sp hybrid orbitals would look like. You have electron density on one side, and you have electron density on the other side that are exactly 180 degrees different from each other. And it would kind of look like that. Whereas a p would be much longer. sp is shorter and has more density closer to the nucleus, like an s orbital would. So it's not as long as a p, but it does have the orientation of a p, where you have some electron density on one side and some electron density on the other side, just like a p orbital would. Remember, they're separated by 180 degrees from each other. One being 180, so this lobe of the p orbital being 180 degrees from the lobe of this. It's the same orbital, but they're 180 degrees apart. So when you mix them together, you get a little bit of both. And so you have one s and one p mixed to form two new orbitals called sp. So what happens is that you have your 1, 2, and 2s, and you have your empty 2p orbitals. So that when you mix them together, you get two new orbitals called 2sp, with one electron here and one electron there. And you see that the energy is sort of in between 2p and 2s. It's a little higher energy than s, but it's not quite the high energy of p. It's the energy is also hybridized. So it's right in between. And so this electron binds with one of the chlorines, 1, 2, 3, 4, 5, 6, 7. And this electron binds with the other one, 1, 2, 3, 4, 5, 6, 7. They come together, and then you get the proper shape. Any questions about how the S and P mix together? You see how it's sort of the sp orbital, it's an average of the two. It's halfway looks like S, and it halfway looks like P. So it has some properties of each one. But the most important property is that it's the orientation. It shows you the shape. You get the orientation you need. You get this linear orientation of one orbital on one side of the beryllium atom and the other orbital on the other side, and 180 degrees apart from each other. Just like you would, because you have two electrons, you want them as far apart from each other as you can, and the furthest part you can get two things is linear, 180 degrees from each other. Let's look at another one. So this again just sort of shows you what I just wrote here. So you have your 2s with your two electrons in it and empty 2p orbitals. And so you make two new orbitals, one from this p orbital and one from this s orbital, and you mix them together to form two new orbitals with properties of both. And as you can see, the energy is in between. It's higher than S, but lower than P. And you still have these two unhybridized, you still have p orbitals, there's just nothing in them. There's no electron density in them because beryllium only has the two electrons, the two bonding electrons. So one goes in one sp, the other goes in the other sp, and there isn't any more electrons left to go anywhere. So then that's it. You only get two bonding regions. And this gives you a little idea of a better idea of what these things really look like. So if you remember, so S is our sphere, and then P are our balloon animals with a knot in the middle. And so you can see that the SP together looks a little bit like both. It looks like you took a sphere and sort of pulled on it a little bit. You pulled it so that you have a little knot in the middle with some density on one side and some density on the other side. But you can see that most of the electron density is moving away from the nucleus so it can bond. Same with this one. So you have two sp orbitals on opposite sides of the atom being able to bond with another atom on one side and another atom on the opposite side. And so this is what the molecule would look like. So here we have our beryllium. Here's one of its sp orbitals. Here's the other sp orbital. And these are the p orbitals that are empty. So there's nothing in them. So we don't have to worry about them. And then here comes chlorine in to bond. Now chlorine has its electron in a p orbital. Those are our balloon animal electrons. They're in the p orbital. And notice that when they overlap, you get good overlap between sp and p. They overlap pretty well. Much better than an s and a p would overlap. An s would look like this, and then when the p would come in like that. So it wouldn't overlap as much. There'd be a lot of empty space in the s orbital. The sp orbital shrinks that down a little bit, so we have more overlap and a stronger bond. So we get a lot of good things coming out of this. We get more overlap and we get the linear shape that we need. Okay, and any questions so far? So SP comes from the hybridization of an S and a P, just one S and one P. A single, or I should say a single S and a single P orbital. So S, hence the title SP. So far so good? I'm going to have to assume that this is all good if I don't hear anything back from you. I'm also checking the chat, so if you guys just want to type things, that's fine with me. Okay, so that's when we mix an S and a P together. What happens if we have three bonding electrons? So here we got boron, our good friend boron. So this is what the isolated boron looks like. It has two electrons in the 2s. It has one more electron than beryllium. So beryllium is element 4, boron's element 5. So boron has 5 electrons, and 3 of them are used for bonding. The 1s electrons down here aren't involved in bonding. They're not valence electrons. So it has 3 valence electrons, 2 here and 1 here. And when, you remember, when boron forms a molecule like boron trifluoride, do you remember what shape it was?
Triagonal planar.
Yeah, it's triagonal planar because it has 3 regions of electron density. And the maximum distance you can get between 3 regions of electron density is on a plane and 120 degrees from each other. That's the maximum distance you can get from those 3. So that's the shape it takes. But just like the beryllium, that isn't the shape, or carbon, that isn't the shape of its atomic orbitals. The shape of its atomic orbitals are, we have 2 in a sphere, and we have 1 in a p orbital, or a stretched balloon, 180 degrees from each other. Well, that doesn't work for 120 degrees at all. So what happens, and we have 3 bonds that are identical. So we need 3 electrons in identical orbitals in order to form 3 identical bonds. That's how it works. If we can't have three identical bonds if we have electrons in different orbitals with different energies. That doesn't work. So now that we have three electrons bonding, we need to have three different orbitals. And so in this instance, we take the 2s down here, and now we need 2p orbitals because we need three places to put electrons. So we take the 2s and we take 2p2. We take two of those p orbitals and we mix them together. And so we have sp2. So we call this sp2. For the reason there's one of the orbitals used for the hybridization is s, and two of them are p, so we just say this is an sp2 hybridization. So we get rid of the 2s and we get rid of two of the 2p orbitals and make these three new orbitals called sp2. And notice that also the sp2 is a higher energy than s, but slightly lower than p. Notice that the energy is slightly higher this time. It's getting closer to the energy of the p, because now we have two p orbitals rather than just one. And so the average energy is slightly higher and closer to the p orbitals. So this gives us three identical orbitals for bonding. And what shape is that going to take? It's going to take the triagonal pyramidal, or the triagonal, a triagonal planar shape. It'll take that planar shape with 120 degrees between each one. Because, as we learned from Vesper before, we were learning about different molecular shapes, that is how you put three regions as far apart from each other as you can. So now we have sp2 orbitals, which look slightly more like p this time. So we get the same sort of shape as we did with sp, but even like a little scrunched down because they're looking even a little more like p now. And so we have overlap between the 2p bonding electrons, valence electrons in fluorine, and the sp2 electron from boron. You get this overlap and you get a bond. You get a strong bond, you get the overlap, and you get the shape you're looking for. A planar with 120 degrees between each one. Okay? Let's move one more. What if you have 4 electrons? Okay, well, if you have 4 electrons, like with carbon, and here's what I talked about this morning. Now that I have 4 valence electrons, I need 4 orbitals with identical energy and identical orientation to each other. Well, how do I do that? Well, if I need 4 orbitals, I'm going to take, I'm going to take all the p electrons, all the p orbitals, and the 2s. I'll take all of them, because that gives me a total of 4, right? There's 3 p orbitals, there's 1 s orbital. I'm going to take all of them and mix them together and make sp3, because I have 3 p orbitals this time. That gives me room for 4 electrons in orbitals that are identical to each other. And now notice that the sp3 energy is almost the same as the p energy. Yes, Ferris?
Wait, so you have 3 sp3 orbitals because you have 4 sp3 orbitals because you have 4 identical hydrogens?
You have 4 identical bonding electrons in the carbon. That's basically what it comes down to. This carbon is going to make 4 bonds, and they're going to be identical to each other. So what it needs in order to do that is to have 4 electrons to all be identical to each other and to be in separate individual orbitals so that they will have 1 electron to share with another atom. And so what happens is then hydrogen comes in and it puts one of its electrons there, 1 there, 1 there, 1 there, and now you have an octet.
I see.
You see? Yeah.
Yeah, I think it's easier
So,
visually to see it as like a Lewis structure, but that picture also helps. So
yeah, so you need to have four places for bonding electrons to go because you're going to be making four bonds. So you got to have those four places to put them. And since you're making four identical bonds, this we'll come back later to show that double bonds are not the same as single bonds, and we'll see why. But now we're making four identical bonds. So we need to have four orbitals that are identical to each other, all with one electron in them. And to do that, we need all the p orbitals and the s orbital because we need four places to put them. And so that's what we do. And we call this sp3. And when you have four regions of electron density that are equal to each other, what shape does that take? Well, we've already learned that takes a tetrahedral shape. And that's where the tetrahedral shape comes from. By mixing those four electrons together and putting them in separate orbitals, four separate orbitals, gives us the tetrahedral shape. So what you see, basically all we're doing is we're figuring out how many places do we need to put electrons? Well, that's how many orbitals we're going to need. And then we mix S and P, and as you'll see, D. We just take as many orbitals as we need to put those electrons in and make them all the same energy. Okay? So far we can mix 2, we can mix 3, now we can mix 4. Let's see what happens when we have ammonia. Now, nitrogen has one more electron than carbon. So notice here we have 1, 2, 3, 4, 5 valence electrons. But there's 4 places we need to put electrons, right? Because we have this lone pair. And we can't neglect the lone pair. That is a region that's going to have electrons in it. So we have to remember to have a place for that too. So what we're going to need is 4 places to put electrons again. So we do the same sp3 hybridization that we did with carbon. But notice the difference this time. So I take my 1s and my 3 p's. That gives me 4 bonding orbitals. When I mix the 1 and the 3 together, I get 4 bonding orbitals. So here's my sp3 orbitals, and I add them just like we added them with atomic orbitals. We go 1, 2, 3, 4. Oh, wait, there's 5. We go back and we put the 5th one in. And when we put the 5th one in, look what happens. We have a lone pair. That orbital is filled. So that won't be bonding. These 3 will. 1, 2, 3. Those are bonding orbitals. Why? Because they have a single electron that needs to be shared. The other one has 2 electrons in it, and so it won't be shared because it already has a paired electron, one spinning up, one spinning down. It's not going to get shared. That will be the lone pair, and that's this lone pair right here. So you have to remember how many regions, not just how many bonds, how many regions of electron density there's going to be before you figure out what the hybridization is going to be. So even though this nitrogen only makes 3 bonds, then you would immediately think, oh, 3 bonds, so sp2, right? We have to remember that there's a lone pair as well. That's another region of space that needs to have electrons in it, and so it has to be sp3. So you see how we add them one at a time, like according to Hund's rule, just like we did with atomic orbitals. When we were filling up p orbitals, we went 1, 2, 3, and then back to the beginning, 4, 5, 6. We do exactly the same thing here because the orbitals, we treat them exactly the same way. We go 1, 2, 3, 4. With carbon, we were done. And they all had a single electron in them. But now with nitrogen, there's an extra one. Boom. That gives us our lone pair. Now,
And
yes,
excuse me?
go ahead.
And I mean, do we have to hybrid them in nitrogen because we already have filled p orbitals?
Yes, but it doesn't give you the right shape. If you did, that's a great question. If you did just, yeah, I mean, you already have 3 bonding electrons in p orbitals. But if you were to use those, you would have a shape that looked like this. You would have all 90 degrees to each other in a lone pair. That would be planar,
Okay.
but it's not. It isn't a planar molecule. It's trigonal pyramidal. So it doesn't account for the shape. That's a really good question. And that's why we know we have to have hybridization for this too, because it's responsible for the shape.
Okay.
So let's add one more electron. Let's go nitrogen 7, let's go to 8. Let's go to oxygen. So oxygen has 6 valence electrons. So here's our 6 valence electrons. We've got 2 in S and we've got 4 in P. So we're looking, think, well, oxygen's going to make 2 bonds. So you could either make these 2 bonds with these 2 P's, but then that doesn't give you the right shape, because those, remember, are at 90-degree angles to each other, and we know it doesn't happen that way. So what else do we know? Well, with water in this instance, how many regions of electron density are there around the oxygen? Taking together both bonds and lone pairs, how many regions are there around oxygen? Electron density regions.
4 regions.
4. 2 of them are bonds. 2 of them are bonds to hydrogen. That's 2. So AX2. But there's also E2. There are these 2 lone pairs. 1, 2. So that's 4. 4. I can count to 4. So there's 4 regions of electron density. So we need 4 orbitals to put them in to get the right shape, because they have to be in the right orientation, 109 or so degrees apart. That gives them the maximum distance from each other. So we do sp3 again, but this time we've got 6 electrons to put in them. So we go 1, 2, 3, 4 all the way across, and then we go back to the beginning, 5, 6. And so these 2 are going to be our lone pairs. And 1, 2, the ones that only have single electron in them, those will be bonded to hydrogen. 1 hydrogen will bond here. Whoops. 1 will bond there, and the other will bond there. So I could probably make that a little darker. Here we go. 1 bonds there, 1 bonds there. Those are the 2 hydrogens. And so you get this shape. You get the overall sort of tetrahedral geometry that comes with sp3. sp3 will always give you a tetrahedral geometry because there's 4 electron regions separated by the maximum distance. That's going to be tetrahedral. But we know that this is a bent shape because it's AX2, E2. So it's the tetrahedral overall geometry, but the shape is dictated by just the atoms themselves. And so when you look at just the atoms themselves, you get a bent shape, okay? Now, when you start to add 5 and 6 regions, it starts to get weird, but kind of fun too. So let's do 5. Now, phosphorus has 5 electrons. 2, 3, 4, 5. And in this phosphorus pentachloride, it's going to make 5 bonds. Well, we've kind of run out of orbitals because I have 1s and I've got 3p. That's only 4. What am I going to do? Well, luckily, phosphorus is in period 3. It has, yay, empty d orbitals. And this is where we can place extra electrons. We can hybridize one of the d orbitals as well. So yes.
Why it doesn't go to 4s orbital first?
For the shapes. The 3D is lower energy than 4s, I believe. Or is it? I don't think it gives us the shapes available. Oh, because we want to stay in the same region. 4s is much further away. D is much closer. So we want to keep the electrons close as possible to make stronger bonds. We don't want to have them really, really far away. So we mix 1s and we mix 3 p's and we take one of these d's for a total of 5 new orbitals, all the same energy. And so you see we call this sp3d, and we put 1 electron in each one. So we have 5 bonding electrons, 5 valence electrons. We have 5 sp3d orbitals, and we put them all there. So now you need D's once you need d orbitals once you get past 4 places, because remember, s, that's just 1 orbital. P, that's 1, 2, 3 more. That's only 4. That's a maximum of 4 areas of electron density. If there's 5, we've run out of S and P. So now we need to start adding D. So now that we have 5 regions of electron density, the shape that takes is trigonal bipyramidal. Like we've learned, that's AX5. And so these are what the orbitals look kind of, strange, but you have the right shapes, and they overlap with the 5 chlorines. 1, 2, 3, 4, 5. Okay, so basically all this is just figuring out how many regions of electron density do I have, and how many orbitals am I going to need to account for all those. So this is 5. When we go to 6, we just need another d orbital. So this is sulfur. So sulfur, we know, oxygen is in group 6, but it only goes up to, it's only in period 2. So it does not have d orbitals. So can't do this. Sulfur is 1 row down. It's in group 3. It has access to d orbitals now. So sulfur can make 6 bonds where oxygen can't, because sulfur can do this. Sulfur can take its 6 electrons, 2, 4, 5, 6, and hybridize them so it has 6 different orbitals, all the same energy. But to do that, it needs 1s, 3p, and 2 d orbitals, add up to 6. And we just call these sp3d2. And now that we have 6 orbitals, the shape that takes in order to minimize overlap is octahedral, just like you would find with AX6. Okay, so just to review, and then we're going to go over this again on Thursday and a little more this afternoon. So just a quick review. These are what the different orbitals are going to look like. So if I need linear, I'm going to take 1s and 1p because I have 2 regions. 1, 2. I need 2 orbitals mixed for those 2 regions. So I take an s and a p. If I need 3 regions of electron density, I'm going to take 1s and 2p for my 1, 2, 3 regions of electron density. 4. 1, 2, 3, 4. I need 4 orbitals this time. My 1s and all of the p's. What if I need 5? 1, 2, 3, 4, 5. Well, then I'm going to have to start adding a d in there for 5. And then finally, when I have 6, 1, 2, 3, 4, 5, 6, then I'm going to need s, 3 p's, and 2 d's together to make that orientation. Okay? So, yes, go ahead.
There's an error here.
Where's that?
Where I can draw. The second line, just for the linear hybrid orbitals formed, it says 2p instead of 2sp.
Oh, you're right. Yeah, okay. I'll change that. Yeah, it should say 2sp. Right. Okay. But you can see it's all based on how many regions. So you have to remember how many bonds and how many lone pairs. You have to, both of those are important because they're each regions where electrons are going to be. And so by doing this, we move electrons to the place we need them to make the shapes that we actually see in nature. If we didn't know what the shapes of molecules were, and for many, many years, scientists couldn't figure out what shapes these were because they had no way to measure them, measure the bond angles or the bond distances. They didn't know. So for years and years, people thought that methane was flat. Thought methane was planar because that made the most sense. But then it was figured out a little over 100 years ago that it's not. That it's actually has that tetrahedral shape, and that's what started people thinking, oh, we can't have tetrahedral and the atomic orbitals the way we think about them now. We're going to have to change the way these things work. And then this was one way to figure out how to do that. So basically, this is just a way to take what we've learned with quantum mechanics and then mix them with what the actual molecular shapes are and put them together in a way that actually makes sense. And this accounts for, like, as I mentioned, about 99% of the properties. We'll see that it doesn't account for all of them. And that's why there's another way of looking at it. But for the 99 times out of 100, this model works perfectly for figuring out where what the bond angles are, where the lone pairs are, everything else. Okay?
Are you able to put that chart on like an announcement, or is it just in a slide somewhere in the?
It's in the slides for
chapter 5.
I've already put it in chapter 5. What I'll do is I'll pull it out. I'll make the correction, and I'll post it on Canvas. Because you don't have to memorize this stuff. What you do have to remember is how many regions of electron density am I going to need? 2, 3, 4, 5, 6. How many am I going to need? And then the chart will tell you what hybridization is that. But yeah, you don't have to memorize all the different shapes and everything. I do want you to know how many different regions. Okay, so let's look at some of these questions. Okay. So does everybody have the recitation for today in front of them or close to them or in an adjacent room or something?
Yeah, I have it.
Okay. All right. So This first question, actually, I'll go over it with you because it gives some really important stuff that we're going to learn a little bit later. But, so, linear molecules. So let's just, first of all, let's just draw CO2. You should be able to draw CO2 in your sleep at this point, hopefully. So carbon goes in the middle, oxygen on this side, oxygen on this side. So how many electrons am I going to need? Yes, 16. So 6 for each of the oxygens and 4 for the carbons for a total of 16. I've used up 4 in bonds, so that brings me down to 12. So let's decorate. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's all my electrons. Then I count and make sure everyone has an octet. So I know the oxygens have an octet because I just gave it to them. They got 6 in lone pairs and a bond. That's 8. They have an octet. So both the oxygens are happy. What about the carbon, though? Does the carbon have an octet?
No.
How many total electrons does it have?
Only 4.
Yeah, it's only got 4. It's got those 2 bonds, one on one side, one on the other. So that's not going to work. So how do we cope with that?
From each oxygen, so for the oxygen from the left, bring over a lone pair to make a double bond.
Mm-hmm.
Do the same thing for the oxygen on the right.
That's right.
And then that gives them a balanced molecule because carbon is only supposed to have 4 valence.
Yeah, so now everyone is 8, so everyone's copacetic. So that's what take those out. So that's what the carbon dioxide is going to look like. We've got a carbon in the middle with 4 bonds. We have an oxygen on one side with 2 bonds and 2 lone pairs. And the other oxygen also has 2 bonds and 2 lone pairs. And the more you draw these, the more you'll see that these things have a pattern. If there's no charge, generally, carbon's going to have 4 bonds and no lone pairs almost all the time. And oxygen is going to have 2 lone pairs and 2 bonds almost all the time. So if you can put those 2 things together, that works pretty well. The question is, how many regions of electron density are around the central carbon? So here we're filling out, we're doing carbon right now. What's the number of regions of electron density around the carbon?
2.
2. Yeah, we have 2. 1, 2. They're double bonds, but there's still only 2 regions of electron density. There's more density. Remember, there's twice as much density in a double bond as there is in a single. So there'd be twice as much density, but it's still only 2 regions of density. So what hybridization are we going to need for 2 regions of density?
SP.
SP. Remember, the number of regions of density are exactly the same as the number of orbitals you'll need. So for 2, SP. For 3, S, with 2 P's. For 4, S, and 3 P's. S and 3 P's. For 5, S, 3 P's, and a D. So that's how you figure out which kind of hybridization you'll need. So for an unhybridized atom, how would I fill in my 4 electrons for carbon here? So here I've got 2s and 2p. Where do my 4 electrons for an unhybridized carbon go?
And that means that they're not overlapping?
No, I just have a carbon atom just sitting all by its lonesome, very sad, nobody to hybridize with. Where would its 4 valence electrons go?
2 of them would go into 2s.
Mm-hmm. Where do the other 2?
One of them would go in one orbital, and then another one pointing up would go in another one.
Right. So here we need to do an sp hybridization. So what would our orbitals look like for an sp? Now remember, that takes out this s and one of these p's. So what do my 3 orbitals look like, or what are my 4 orbitals? I'm still going to have the same number of orbitals before and after, but what are my 4 orbitals going to be after hybridization? Because remember, I want to do sp hybridization. And the total number of orbitals does not change. I had 4 before hybridization. I'm going to have 4 after.
2 sp orbitals.
Yep, I'm going to have 2 sp orbitals. 1, 2. And what else am I going to have?
2 p orbitals.
2 p orbitals. 1, 2. So the p orbitals don't change. These 2 p orbitals are unaffected. So I still have them. They're still there. And I've got my s orbital's now gone. So this one's gone, and this p orbital's gone. And I've replaced them with sp orbitals. So those are going to be a little bit higher energy than s, but not as much as p. So this will be an intermediate energy between s and p. And these 2 p orbitals will be the same as they always were. So now I have, let me erase my old CO2 molecule. Okay. So I still have 4 valence electrons. That doesn't change. So 2 things don't change. I have the same number of valence electrons as I had before. And I have the same number of total orbitals that I did before. They just sort of move around a little bit. So now instead of having this orientation over here, I now have this orientation over here. I still have 4 electrons to put in them. Where do I put them? Where do my 4 electrons go?
All in.
I'm pretty confused, Professor. So I'm just guessing. Would 3 of them go in the sp and 1 of them in the p?
No, remember, we need to make 2 single bonds with the oxygen, and we needed to make 2 double bonds with the oxygen. So we'd have a single bond on each side, and then we need to have a double bond on each side. So we have to have, so our hybridized orbitals are for making that first bond. So we're going to put 1 electron in each one. 1 there and 1 there. This will make the first single bond with 1 oxygen, and this will make the single bond with the other oxygen. Anyone know what single bond, another thing we call single bonds is? There's another word for them. We haven't learned it yet. Don't worry if you don't know it. I was just wondering if anyone remembered. There's 2 different kinds of bonds between elements. They have 2 different names. Do you remember what the single bond was called?
Delta.
Not delta. You're close. It's a Greek.
Sigma.
Sigma. Yeah, sigma and single. So those are called sigma bonds. So the single bonds are called sigma bonds. And those are always the bonds that are made first. The other thing we'll learn is that sigma bonds are made with hybridized orbitals. So So our sigma bonds are made with the sp orbitals. So those are my 2 electrons. My first 2 electrons go in the sp, the other one goes in the sp. Those will make single bonds. I got 2 electrons left. Those go in the p orbitals. 1, 2. What's the other bond? Do you have sigma bonds, and what's the other one? Do you remember?
Bond,
Hmm?
delta bond,
No, not a delta. Ryan's got it. What is it, Ryan? Sigma, and what's the other one called? Are you shy today or something, man? What's going on? Ryan's shy. I thought that seems weird, but yeah, pi is the other one, pi bond. The second bond made between atoms is a pi bond. The third one made is also a pi bond. So the first, if I have a single bond between carbons, the first one made is called sigma. The second one is a pi. And if there's 3, the one in the middle is a sigma, and the one on top and the one on bottom are both pi's. And the reason why they're called, anyone want to take a guess at the reason why those are called pi bonds with a P sound?
p orbital.
Those are made with p orbitals, exactly. So this p, or this electron in a p orbital makes a pi bond, and this electron in the other orbital makes a pi bond, because pi bonds are made with p orbitals. That's where the sigma and pi come from. Sigma comes from single, and pi comes from p orbitals. So sigma and pi. And a little later on, we'll show you exactly how those work. But right now, what we really want to focus on is what the hybridization gives us. Hybridization gives us equal energy electrons to make those initial sigma bonds. Now, another thing to remember, why you should remember that it's sp, is what shape is carbon dioxide?
Linear.
It's linear, remember? It's linear. And linear is sp. So pretty much any linear molecule, you're going to have sp hybridization. For trigonal pyramidal or trigonal planar, you're going to have sp2. For tetrahedral, you're going to have sp3. Okay, so that's how you would do. That's the hybridization for carbon. Okay, carbon will give you 2 electrons in sp orbitals and 2 electrons in p orbitals. That's necessary for carbon because it has 2 regions of electron density around it, sp. But that's going to be different for oxygen. So let's do oxygen this time. So how many valence electrons does oxygen have? 6. So so this is on the left, these are for the unhybridized orbital. So we have S and we have P. Where are the electrons going to go? We have 6 of them. So just regular old electrons in unhybridized atom. Where do we put the electrons? We have 6 to put there. Where does the first one go? First electron. Do I put it in a P? Do I put it in an S? Do I throw it out the window? 2, Ariana, right. 2 go into 2s. 1, 2. And where do we go from then? From there? I got 4 left. One electron in each p. Very good. So I got 1, 2, 3. Where's the 4th one go? Let's put it anywhere. Nice. Yeah, I'll just put it here. Right. So that's the situation in the unhybridized oxygen. Oxygen is hanging out by itself, looking for a partner, aren't we all? And so it has its electrons like this. Now, let's go back to the CO2. This is what the oxygen looked like in the CO2. How many regions of electron density are around the oxygen this time?
3.
3. 1, this lone pair. 2, this other lone pair. 3, this double bond. So it has 3 regions. So if I have 3 regions, if I have 3 regions of electron density, what hybridization do I need to do that? Man, nobody wants to talk to me today. I'm very sad and lonely. Everyone just wants to type. Right, 3 regions, sp2. Right, so we need 3 regions of equal energy, 3 regions where we're going to put electrons. So that means we're going to need 3 new orbitals that are identical to each other. So I need 3. So I take 1. Oops, let me go back. I take 1, 2, 3, which means sp2. So I have 1 s and 2 p. So I'm going to put them here. 1, 2, 3. So higher, and remember, this will be important later. Higher energy than S, lower energy than P. So these are my sp2. Do I have any other orbitals left? Remember that your total number of orbitals has to stay the same before and after hybridization. You have to have the same number. So do I have any orbitals left over?
The p orbital.
Mm-hmm. How many p orbitals?
1.
1. So I've hybridized 3 orbitals together, leaving 1 left over. So the one that's left over is this p orbital here. Still have the same number of orbitals, still have the same number of valence electrons. They're just going to be in different orientations than they were before. So where am I going to put them? First of all, how many electrons, how many valence electrons am I dealing with?
6.
Still got 6, exactly. Still got the same number. That hasn't changed. So 2 things don't change. Number of orbitals don't change. Number of electrons don't change. The only thing that changes is where is their orientation. That's it. That's really all we have to remember. All we're doing here is changing the orientation of these orbitals from in the atomic shape, where they were one particular shape, into a molecular shape where they're different. That's all we're doing. We're just moving them around. So the number of orbitals and the number of electrons stays identical. And we fill them using the same rules we did before. So where am I going to put my electrons?
Filling 3 electrons first.
Yep, 1, 2, 3.
Professor, if we're using the same rules as before, don't we fill in all of sp2 before we move on to P?
Well, remember, we have 3 regions of electron density, and how many bonds is oxygen going to make? So remember, oxygen look like this. How many sigma bonds is oxygen going to make?
1.
1. So one of these sp2s has to stay with just 1 electron in it.
Okay.
Yeah, so one of them has to stay basically with 1 electron. So what we'll do is go 1, 2, 3, 4, 5, and then the 6th one's going to go here, because this is required to make our sigma bond. This is required to make our pi bond. So remember, the first bond is sigma, the second one is pi. So we have to have 1 electron in the p to make the pi, and we have to have 1 electron in one of the sp2s to make the sigma. And then this is one of our lone pairs, and this is the other one. So that accounts for all of our electrons. Okay? Yeah,
Okay.
go ahead.
And why did this time do we use sp2?
Because there's 3 regions of electron density around the oxygen. There is 1 lone pair, 2 second lone pair, 3 double bond. So there's 3 regions of electron density that we have to account for.
So if there was a 4th, and then we would just add the other orbital?
If it was a 4th, then there would be sp3. Yeah. Like with water. With water, we've got, so with water, we have 4 regions of electron density. We have this lone pair, that's 1. We have this lone pair, that's 2. We have this single bond, that's 3. And we have that single bond, that's 4. And so in that situation, we would have, where's my draw? Here we go. So when we need 4, we would do 1, 2, 3, 4 sp3. And we would fill in our single electrons one at a time. 1, 2, 3, 4, 5, 6. That's one of our lone pairs. That's the other lone pair. This forms a sigma bond with 1 nitrogen. This forms the other sigma bond with the other nitrogen. So a couple things to remember. Sigma bonds, the first single bonds or sigma bonds, that's like the first bond that's made between, are always made with hybridized electrons. So either if it's in sp or sp2 or sp3 or whatever it is, those single bonds are made with hybridized orbitals. And p orbitals are used to make every subsequent bond, pi bonds. So if you need to make a double bond, you have to have 1 electron in a p orbital. If you make a triple bond, you need to have 2 electrons in p orbitals.
So this has more to do with bonds and not really the orbitals?
It has more to do with the orientations required. Yeah, it has to do with molecular shapes. The shapes of atomic orbitals do not account for the shapes of molecules. And so we figured out that, well, atomic orbitals must be one shape and molecular orbitals have to be another shape, because they can't be the same. Atomic orbitals are all the wrong shapes for making these molecules.
Okay, and sorry, one more question. Are we ever going to go past P, or is there a reason we just stay between S and P orbitals?
No, when we need 5, if we need 5 regions, that's
Okay.
sp3d, and if we need
Okay.
6 regions, that's sp3d2.
Okay.
We just keep grabbing orbitals depending on how many regions of density there are. If there's,
Okay.
we can just use S and P up to 4, but then we run out of orbitals. There's no more orbitals after 4. There's 3 P's and there's 1 S. That's 4. That's it. So in order to do 5 or 6, this is why we were talking before about atoms that can violate the octet rule. This is why. That's why they can violate the octet rule, because they pull down extra orbitals and put electrons in them. That's where this is where that comes from. This is how that happens. So we're just finally learning why the hell it can do that. This is why. All right, so is everyone clear on the different hybridizations? I mean, you don't have to get all of this at once. Obviously, there's a lot going on. But for the first two, I figured that we could do that together. So what about any other questions so far? Who's had a chance to look them over? I don't want to sit and do the whole thing if you guys. Oh, number 5. Want to do question 5? Let's have a look. Um, 5.
Professor?
Yeah.
So for this number 5, for each one, are we basically doing 1 and 2, those steps over again for each one? Like what we did for question 1 and 2? To figure it out?
You don't, well, for this one, you don't have to put all the orbitals in here. Basically, all we're looking for here is can you figure out, based on the shape, what the hybridization is. Like for instance, here we have sulfur hexafluoride. So we've got sulfur with 1, 2, 3, 4, 5, 6 fluorines. So it has 6 bonds. How many regions of electron density surround that sulfur?
6.
6. So we know that its geometry is octahedral. We know the shape itself is octahedral because the sulfur doesn't have any lone pairs. What hybridization do you need for 6 regions? So sulfur is going to need 6 bonding electrons to make those 6 bonds. So it needs 6, needs 1, 2, 3, 4, 5, 6 orbitals, all with 1 electron each in them. How's it going to do that? So each one of these electrons gets shared with a fluorine to make the 6 bonds. What hybridization is that? You start with S. So how many orbitals in S?
1 orbital.
1. And then we go to P is next. How many orbitals in P?
3.
3. Well, we're going to need 2 more. So once you get past P, where do you go?
D.
D. And how many D orbitals are you going to need?
Just 2 more.
2 more. That's right. You just add them together. 1 plus 3 plus 2. sp3d2. It's not as scary as you know. I mean, I make it out to be a little scary when you're putting when you're actually writing the orbitals out. It gets a little weird. But the thing to remember is how many regions of electron density. That is the number of orbitals you're going to need. That's what it really boils down to. So NH3, ammonia. So when we draw ammonia, Again, this should be one of those things you can do in your sleep by the end of the class. Ammonia looks like this. Or if you want to put the, whoops, where'd she go? What the hell happened there? Oh, okay. If I touch the edge of my screen, it goes haywire. Here we go. Ah! Okay. So one coming out, one coming out, one going behind. So that's the shape of ammonia, trigonal pyramidal. So it has how many regions of electron density around the nitrogen?
4.
4. You can just count them up. It's got 3 bonds. It's got 1 lone pair. So we need 4. 1, 2, 3, 4 places to put electrons. So what's that going to be? What hybridization is that going to be?
sp3.
sp3. That gives us all we need. And so nitrogen has 5 valence electrons. So we go 1, 2, 3, 4, 5. So there's our lone pair. And those are that one bonds with a hydrogen, that one bonds with a hydrogen, that one bonds with a hydrogen. So sp3. And basically, so that's just really how you go. This table you can get through pretty quickly that way. Is there, I know, I want to save the one for last because we haven't talked about oxidation numbers in a while. But
Professor?
you want to do one of the ones on 3? Yes, go ahead.
Well, just to avoid confusion for me, will there ever be a molecule that's lined up iodine, carbon, and then iodine? For I just don't get it confused with iodine chlorine molecule, because it's
Oh yeah. For the third one there.
yeah. Will it ever be like iodine, carbon, iodine, or is it always going to be iodine and chlorine together? Where I don't have to worry about.
Well, if it's iodine and carbon together, it would be, oops, damn it. That would be this.
Okay.
So yeah, it would be capital I. So with chlorine, you have a capital C and a small L. So iodine is always going to be capitalized.
Okay.
Yeah. So if you see a capital I and then a capital C after that, look for the next letter. If it's an L, that's chlorine. If it's a C, that's by itself. That's carbon. Oops. Damn, spilled some tea on my computer. That's not good. Can we do one of 3, Ryan? Which question are you talking about? Give me a heads up. This one? Okay. Yeah, it's a good one. So, yeah. Oops, let me go back. So as I mentioned, the first single bond made between atoms is a sigma. So if there's only a single bond, like between, let's say, carbon and hydrogen, that's a sigma bond. That's it, we're done. If we have a double bond between carbon and oxygen, for instance, we have 1 sigma and 1 pi. If we have a triple, like between 2 nitrogens, then we have a sigma in the middle and a pi on top and a pi on the bottom. So sigma and 2 pi's. But the first bond is always sigma, okay? So let's count up. Let's take the first one. Let's do the first one together. So this is acetic acid. This is vinegar. So the first thing we need to do is actually get all the bonds right. Make sure we have enough bonds. So look here, and do you see any atoms that don't? Let's just add electrons where we need them. obviously oxygen is going to need some more electrons than it has, because oxygen has 6 valence electrons, right?
And
So-
carbon has a double bond.
So where are we going to find a double bond?
Between 3 and 2, or it could be between 3 and 1.
Okay, so if we put a double here, that gives carbon 4 valence electrons. That's good. So how many more lone pairs is that oxygen going to need?
2 more lone pairs.
2 more, right? 2 there, 2 there. What about oxygen number 2?
Two more lone pairs.
Yep. So if you're wondering, it's like you're thinking to yourself, well, how does he know that one is double bonded and that one isn't? Remember my sort of, the take home rule: carbon, 4 bonds, no pairs. Nitrogen, 3 bonds, 1 pair. Oxygen, 2 bonds, 2 pairs. Fluorine, 3 pairs, 1 bond, almost all the time. So if you see, for instance, oxygen 2 here already has 2 bonds. So it's unlikely it's going to make 3. So oxygen almost always makes 2. So if you have an oxygen already making 2, all it needs is 2 more lone pairs. So you put them on there and that oxygen's happy. However, this other oxygen is only making 1 bond. Give it another one. So it makes 2 and 2 pairs. So now both oxygens have 2 bonds and 2 lone pairs. So let's answer some of these questions. So atom number 1 is oxygen. It's our oxygen 1. It doesn't have any bond angle because it's just bound to 1 atom, so there's no bond angle there. So what's the hybridization on that, on our oxygen 1? How many regions of electron density? Therefore, what's the hybridization?
There's 3 regions, so would it be sp2?
That is right. sp2, because it has 3 regions of electron density. So we would go 1, 2, 3, sp2, and then it would have a p orbital left over. So 1, 2, 3, 4, 5, 6. Here's 1 lone pair. Here's the other lone pair. This sp2 makes a sigma bond with carbon, and this p electron makes a pi bond with carbon. So since it's a double bond, it has 1 sigma and 1 pi, okay? So total, how many sigma bonds and how many pi bonds do we have in acetic acid? We count them all up.
1 sigma bond.
Nope.
7 sigma bonds?
So let's count them. 1, 2, 3, 4, 5, 6, 7. Right, 7. And there's only 1 pi bond. If there's only 1 double bond, there's only 1 pi bond. So for every double bond, there's a pi. For every triple bond, there's 2 more pi's. But they all have a sigma bond. So you count every single bond, no matter whether it's double or triple or single. You count all of them. That gives you the number of sigma bonds. Then you go back and see how many are doubles and how many are triples, and then total those up, okay?
Excuse me, Professor.
Yeah.
Is there a reason on the orbitals that you just erased that the spins?
Oops.
That's fine. That the spins were all going the same way?
Yes, because when you, here we go. There we go. Yeah, when you, oh, sorry, no, I screwed that up. Yeah, that's my,
Oh, okay.
that's my bad. Yeah, these should have been the other way.
Okay.
Good, nice catch. Yeah, those should have been like that. Yeah,
Okay, cool.
my bad. Nice call.
Where
Someone's
does
paying attention. I love it. Yes.
where does that leftover P come from? And then the 3.
There's 6 valence electrons in oxygen. So you've got 2, 4, 5, 6.
Okay.
Yeah. And so instead of filling all the sp2s, we need to put one of those electrons into a p orbital because we need to make 2 different bonds. We need to make a sigma bond, and those are made with hybridized electrons, and we need to make a pi bond, and that happens with p orbitals. So that's why we fill them up that way. So let's do atom number 2. Atom number 2, oops, I got rid of all my 1, 2, 3, 4. 1, 2, 3, 4. So oxygen 2. Oxygen 2, how many regions of electron density are around oxygen 2? So here's oxygen 2. How many electron regions are around that?
4.
4. Right. So we've got 2 bonds, and we have 2 pairs. So we have 4 regions of electron density. So what hybridization is that?
sp3.
Yep. 4 regions. We need to have 4 places. So sp3. Now the angle, we're looking for this carbon, oxygen, hydrogen angle. So we're looking for this angle here. What is that angle? Now it doesn't need to be precise. Basically, what angle would we expect with an sp3 hybridization with 4 regions? What geometry is that?
I'm guessing before looking at the chart, but with the 2 lone pairs, wouldn't that make it 180 degrees because they're both pushing on each other equally, or no?
No, because remember, what shape is this? We have sp3 hybridization. We have 4 regions of electron density. What geometry is that? 4 regions.
Tetrahedral.
Right. So it's should be tetrahedral. And what bond angle do we associate with tetrahedral shapes?
109.5.
Right. So the question here is this going to be more than 109.5 or less than 109.5? This angle right here. And then here's our 2 lone pairs. So this angle right here, is it going to be more than 109 or less than 109?
Less.
Less than?
Less, right, less, because these 2 lone pairs repel these 2 bonds away from it and it pushes them slightly together. So it's going to be bent and the angle is going to be less than, so we put down less than 109.5.
Oh.
And then so for 3, that is the carbon. So carbon number 3. So what is going to be the hybridization around carbon number 3? How many regions of electron density are around carbon 3?
3.
3, right. It's got 2 single bonds. 2 single bonds. It's got 2 sigmas, and it has another sigma and pi for a double. So it's got 2 single bonds, and it's got a double. 3 regions of electron density. So what hybridization is that?
sp2.
sp2, man, Guys are picking up on this quickly. Yeah, sp2 for 3 regions. So with sp2, what shape is that? 3 regions.
Trigonal planar.
Planar, trigonal planar. So what's the bond angle associated with trigonal planar?
120.
120. So either this carbon, carbon, oxygen bond. So that's the bond angle we're looking at, this one here. Is that going to be more than 120 degrees, or is it going to be less than 120 degrees?
More, or like just 120 degrees, since there are no lone pairs.
There's no lone pairs, but is it equal all the way around? Is it completely symmetrical all the way around? You only get that 120 degree perfect angle when it's absolutely the same all the way around. But is it?
No.
No. What's different about it?
The double bond.
Exactly. We've got a double bond here. We have a single bond there and a single bond there. So it's not completely symmetrical. So what effect does that double bond have on this angle right here?
Less than 100 degree.
Less than 120. Yeah, it squeezes them together because remember, there's twice as many electrons in this area as with a single bond. So since there's twice as many electrons, it has more repulsion force and it pushes those other 2 bonds away. And so this angle will be a little less than 120, so less than 120.
Professor?
Yeah.
I'm looking at the Axe body spray chart.
Okay.
Is there an example of when the angles are going to be more than? Because I just keep seeing less than.
Well, it depends on which angle you're looking at. So let me go someplace. Okay, you clear this out. So if you're looking, it depends on the angle. So it's, for instance, the last one we just looked at. So because we have a double bond here, this angle is going to be less than 120. On the other hand, this angle is going to be more.
Yeah.
And
but,
this angle is going to be more. So basically, anytime you have more electron density on one side, it makes the angle between that increased density and the other regions greater, and it pushes the 2 regions without the increased density closer together. It makes that angle smaller.
So
that's,
we want to.
That's always going to happen. Either there's going to be lone pairs up here, or there's going to be a double bond up here, or something to push these 2 closer together.
So we want.
I can't think of anything that's going to like bring them closer.
Okay, so we want to know the angle of the least dense area of the
no, that's not true. I can think of one thing. So if we have hydrogen and like iodine and iodine and iodine, basically these iodines are pushing each other away because they're such big atoms. They push each other away and makes this angle smaller than 109.5. So I mean, that's an example. If you have something smaller on one side, yeah, it gets squished together.
Okay, so if we go back to the acetic acid, like, how do we know which angle you're asking for? Like, how do we know?
That's a little tricky. Yeah, basically, I'll make that a little more obvious, like on tests and that.
Okay.
Yeah. Yeah, basically you just go in a line. So the line from C to O, would be the angle you're looking for. And a number 2, also a line. That would be the angle from the carbon to the oxygen to the hydrogen. Just going in a straight line. But yeah, I'll make it a little like, yeah, I stole this from somebody else. Yeah, I should have made it a little more obvious than this. At least I put in the NAs for the bond angle, because I remember I saw this on a test and students were just freaking out, like, what's the bond angle of this oxygen? Well, there isn't one, so that's why they were flipping out. So I did change that, but yeah, I should make the bond angle a little more apparent. I'll have like CCO bond or COH bond. That's a really good suggestion. All right, so here you don't even need to put the doubles and triples in here. This is vitamin B2. So this is riboflavin. So you already have all of the doubles and everything in there. What you will need to do is add the lone pairs. So if you see, for instance, a nitrogen with 3 bonds, like this one, it's going to have a lone pair. So include the lone pairs. So carbon will not have any lone pairs typically. Nitrogen, remember, 3 bonds, 1 pair. Oxygen, 2 bonds, 2 pairs. So put in all the lone pairs and then basically count up the ones that have 4 regions of electron density, the ones that have 3 regions of electron density, and the ones that have 2. Okay? Like for instance, that nitrogen that I just circled, once you add the lone pairs, then it has 1, 2, 3 regions of electron density. It's got the lone pair, it's got a double bond, and it's got a single bond for 1, 2, 3 regions of electron density. What hybridization is that?
SP2.
Right, SP2. Yeah, so basically, really all you need to do is just count up the S's and the P's, and that tells you how many regions of electron density there are. SP3, that's 4. SP, that's 2. SP2, that's 3. So, like with practice, it'll come to you, hopefully, a little fairly quickly, that is the reason why we have these hybridizations, because we have those regions of electron density. They need to be the same. How do we do it? Oh, S and 2 P's, S and 3 P's, and so on. Okay, let's look at the last.
Professor,
Yes,
Ryan,
go ahead.
Ryan had a question in the chat.
Oh, I didn't.
It says,
Will linear always be 180? Well, linear means 180. What's the yeah, I mean, the definition of linear is 180. So if I have, this, if I have hydrogen cyanide here, that is going to be linear because I have 2 regions of electron density around the carbon. It is sp hybridized. It's a linear molecule. This angle, this hydrogen, carbon, nitrogen angle is 180 degrees. So is that what you were asking, or? Yeah, I mean, linear, it's always going to be linear because you can't, no matter what you put over here or what you put over there, 180 degrees apart is the maximum you can get. You can't get them any more apart than that. So you can just load up one side with, a neutron bomb of electrons. Doesn't matter. The maximum distance you can get between those 2 regions is 180 degrees. They can't be any more or any less. So yeah, it's always going to be 180. I think that sounds right to me. But yeah, I mean, anything linear, that's the maximum distance. So you can't get better than 180 degrees apart.
So that triple bond wouldn't cause one of the bond angles to be reduced just because it's linear. You can't like move it.
Which one of the bond angles?
You could. I
There's
think that was
only
hydrogen side.
okay. Let's put it up again. Well, there's only one bond angle. There's only the hydrogen, carbon, nitrogen bond angle, because the only thing that's bound to more than two atoms or more than one atom is the carbon. So the carbon's in the middle, and basically what you're asking is what's the angle between the hydrogen and the nitrogen, right? Is that so? Yeah, so it's 180 degrees. So it can't really be anything else. All right. Right, so let's do a quick review of oxidation numbers. Anyone remember the difference between a formal charge and an oxidation number? What's the difference between the two? First of all, how do we calculate formal charge?
Actual valence electrons versus what they have. Is that how you say it?
Yes, well, yes and no. These both involve valence electrons. So let's just do one, and we'll see what the difference is. So formal charge assumes that atoms share equally. So let's make NO2. Let's make nitrogen dioxide. So who goes in the middle? Who am I putting in the middle? Nitrogen or one of the oxygens?
Nitrogen.
Yeah, that's right. Nitrogen goes in the middle because it has lower electronegativity, so it generally goes in the middle. So I'll put an oxygen on this side, put an oxygen on that side, put my sigma bonds in. So remember, the first bond, always a sigma bond, so this will be a sigma, this will be a sigma. So how many total electrons are we dealing with here? Total valence electrons. Oxygen has how many?
So I was a little confused because it ends up being an odd number, but 12 for oxygen and 5 for nitrogen.
Yeah. So 12, oh, yeah, 12 and 5. So 17. Yeah, so this really should have a negative sign on it. But just for grins and giggles, we'll do it this way.
Okay.
So, all right, so 17. So we've got 4 in bonds, so that leaves us with 13. So let's decorate. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So now we figure out who has a octet and who needs to have an octet. So who has an octet?
The oxygens.
Oxygens already do, because we gave them an octet. They have 6 electrons in their lone pairs, and they have another pair in the bond, so they have a total of 8, so they're good. How many total electrons does the nitrogen have?
Only 4. Oh,
Total.
5.
5. It's only got 5. So it needs 3 more to have an octet. So we'll address that by putting that lone pair there and make a double. So now it's got 2, 4, 6, 7, and we'll put double bond there. Oh, wait, but we can't do that. That gives it more valence electrons. It gives more total electrons than it can handle. Oh, now I remember how this works. So, yeah, we can't do that. Why can't we do that? Why can't we put another double bond on the other side?
Does that give you 9 electrons?
Yeah. Well, it gives you 9 electrons. That wouldn't be a problem for another if this was sulfur, or if this was phosphorus, but it's nitrogen. So how come nitrogen can't have 9 electrons?
Because it's in the second period.
Right. So it can't have that many. So we're stuck with this. So let's figure out what the formal charges are. So basically we're stuck with this structure.
Okay.
What is the formal charge? So we got oxygen 1, oxygen 2, and nitrogen. So what's the formal charge on oxygen number 1? How do we calculate that?
There is no charge.
How did you calculate that though?
So it's in group 6.
So it's supposed to have 6 valence electrons, and how many does it actually have?
It has 6.
It has 6. It's got 2, 4, 5, 6. So its charge is none. What about oxygen 2?
It's in the same group,
Mhm.
but it has
So it should have 6. How many does it actually have?
7.
It has 7. It's got 2, 4, 6, and 1 from this for a total of 7. So its formal charge is -1. Now what about the nitrogen? It's supposed to have how many valence electrons?
5.
5. And how many does it have?
4.
4. It's got 1, 2, 3, 4. So its charge is +1. So we've got a charge of +1 on the nitrogen and -1 on the oxygen, and that balances out. That gives you a total charge of 0. So you got to, those are our formal charges. Now, when we calculate formal charges, remember, you assume you just break these bonds down the middle, and that each element gets to share equally, gets to share those bonded electrons equally. One atom gets one of the electron bonds, the other atom gets the other bond of the electron. They share them equally. But when we're calculating oxidation numbers, we don't do that. What we do is we take into consideration the relative electronegativities. And if an atom has a higher electronegativity, it gets all the shared electrons. And the one with a lower electronegativity gets none of the shared electrons. So let's go back and repeat. So, got my oxygen, got my nitrogen, my other oxygen, 1, 2, 3, 4. 1, 2, 3, 4. Now this time, I'm going to figure out what the oxidation numbers are. This gives us an idea of how those electrons are being actually shared in the molecule. Instead of assuming that they're equally shared, we're going to assume that whoever has the highest electronegativity is going to steal more of the electron density. So let's start the same way. So we have oxygen 1, oxygen 2, and nitrogen. So oxygen 1, supposed to have 6 valence electrons. How many would it get now? If it gets all the shared electrons, how many would it get?
Still 6. Oh, so we're including the double bonds in full?
We're including all the electrons. So we've got 1, 2, 3, 4. And oxygen gets all of them.
So 8?
8, yep. So what's the oxidation number on the oxygen?
-2.
Yep. Now let's look at O2. It's supposed to have 6 valence electrons. Let's give it all the electrons, both the ones that it has and the ones that it's sharing. Because remember, oxygen has a higher electronegativity than nitrogen. So how many total electrons will oxygen have this time?
8.
Also 8. It's got the 3 lone pairs for 6, and it has the shared pair. So 8. So what's its oxidation number?
It's going to be the same, -2.
Same, -2. And you will find that 95% of the time, oxygen will have an oxidation number of -2. No matter who it's bound with, no matter how many electrons it's sharing, almost always has an oxidation number of -2. Why? Because it's more electronegative than pretty much everything except fluorine. So it gets to keep all the electrons. So if it has an octet of electrons, it gets to keep all of them for -2. Now let's look at nitrogen. It's supposed to have 5 valence electrons. How many does it get to keep for itself? In this situation?
6. Are we not including the lone pair or the lone?
It doesn't have a lone pair. It just has one. It just has that one electron. Does it get to claim any of the other electrons in the 3 bonds? Does it get to keep any of them?
Yeah.
No, because we gave them all to oxygen, remember? We gave all these electrons to this oxygen, and we gave these 2 electrons to this oxygen. So all poor nitrogen has left is 1.
Well,
It's just got that 1. That's it. And so its oxidation number is +4. And the other thing you should know about formal charges and oxidation numbers is that when you add all the formal charges together, they should equal the overall charge of the ion of the molecule you're dealing with. The same is true for oxidation numbers. So if my first oxygen is -2, my second one is -2, and the nitrogen is +4, I add those all together, 0, which you should get if it's a neutral molecule. So the oxidation number should add up to the same charge as the formal charges do. So if it's a neutral molecule, they should add up to 0. If it's like phosphate over here, they should add up to -3. Do you want to do one more before to see how this works?
Can I ask you a question?
Sure, of course.
So when we're giving the electrons away to one element,
Mhm.
do we always start with the elements on the outside?
No, start with the more electronegative. Whoever's more electronegative, who usually
Okay.
is on the outside.
Okay.
Yeah, so the more electronegative element is usually on the outside. So that's generally where the electrons are going to go when you're counting oxidation number. Generally, the element that's in the middle is going to get oxidized. It's going to have its electrons pulled away from it by who's ever surrounding it. And we can do, let's do the third one, because that's sort of similar to the bonus question on the lab test. So this is S2O3. This is the thiosulfate ion. And it goes like this, SSOO. And it has an overall charge of -2. So how many electrons is the thiosulfate ion going to have?
Sorry, Professor, can I ask you a question before we go on?
No, yeah, no problem. Of course.
Why are you putting it that way and not adding an oxygen to the left of the other sulfur?
Because this is what it looks like.
Okay. Okay, that's fine.
Yeah, I mean, sulfate looks like this, right? Sulfate looks like this. And thiosulfate just takes out one of those oxygens and replaces it with a sulfur.
Okay.
That's the only difference. Yeah. Thio for you budding organic chemists just means sulfur. So a thiol group is just sulfur.
Okay.
So if you see thio in there, it means sulfur. So yes. So how many total electrons am I going to have in my thiosulfate ion? So remember, sulfur and oxygen both have the same number of valence electrons. How many is that?
6.
They both have 6, and we've got 1, 2, 3, 4, 5 of them. So, whoops. So 5 times 6 equals 30 electrons. Any more or less to take off or add?
Yeah, add 2 more.
Add 2 more, because it's got so it's got 32 total electrons. So just go around the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 23, 24. I've got 4, I got 8 in bonds, so I'm done. So that's all the electrons. So now we figure out who has an octet, who needs an octet. So who has an octet, who needs one? Is there anybody with less than 8 total electrons?
No.
No, there isn't actually. But remember, when we're making these sort of structures, we try and reduce the formal charges as much as we possibly can. So now's a good time to calculate formal charges. So what are the formal charges on all the oxygens? Since all the oxygens are the same, and actually the sulfur is the same too, because it also has 6 valence electrons. What will be the charges on all the atoms on the outside? So they all should have 6. How many do they actually have? Valence electrons.
7.
They all have 7, right? So each of them will have a charge
7.
of -1. So -1, minus, minus, minus. And the sulfur in the middle, how many? It should also should have 6 valence electrons. And how many does it have? It has only, yes. How many valence electrons? It has 4, right? 1, 2, 3, 4. So it has 4. So it'll be +2. So how do we reduce the total charges?
You would have to add a double bond.
Give 1 pair of electrons.
So we take a pair of electrons from this sulfur, move it to the middle, and we take a pair of electrons from this oxygen and move it to the middle. Then that gives us double here, a double there, and gets rid of an extra pair of electrons. So now let's look at the formal charges, calculate the formal charges again. So these two haven't changed. So this oxygen is still negative, this oxygen is still negative. But what about the sulfur, the exterior sulfur, this one right here? Now what's the formal charge on it?
There's no charge. There's supposed to be 6.
Yeah, so it's supposed to have 6 valence electrons, and it does. It has 6. So there's no charge there. And the oxygen on the other side will no longer have a charge because it has 2 lone pairs and 2 electrons for 6. So it no longer has a charge. And the sulfur in the middle now has 6 valence electrons from the 6 bonds. It's got 6 bonds now. So 1 electron from each one. So it doesn't have a charge either. So the total charge is -1, -2. That works. Now, let's look and see what the oxidation numbers are. So let me clean this up a little bit. Oops. There we go. So I've got oxygen 1, oxygen 2, oxygen 3, sulfur 1, sulfur 2. So let's do oxygens 1 and 2 first because they're in the same situation. Let's look at our oxidation numbers. So oxygens 1 and 2. So they should have 6 valence electrons. Now remember, they get to keep all of the lone pairs they have and they get to keep whatever shared electrons they have with another element with a lower oxidation number, or sorry, lower electronegativity. Now, oxygen has electronegativity of around 3.5, and sulfur's is like 2.5. So sulfur is less electronegative than oxygen. So oxygen gets to keep all those shared electrons. So for oxygens 1 and 2, how many electrons does it get to keep for itself?
8.
8, right, because it's got 3 lone pairs, that's 6, and it's got a single bond, that's 2 more, so 8. So it has an oxidation number of -2, both of them. Now, oxygen 3 should have 6 electrons. How many does it get to keep for itself?
8.
Same number. See, it's what I was saying before. It's like it almost always gets to keep all 8 electrons. So it's got 2, 4, and there's 4 more electrons and bonds, and it gets to keep all of them. So also -8. So the 3 oxygens are all -2. So -2, -2, -2. What about sulfur number 1? Let's do sulfur number 1. It's also supposed to have, will you two stop it? It's also supposed to have 6 electrons. How many does it get to keep for itself?
2.
How many?
2.
2, right, because it doesn't get to keep any of the electrons with the oxygens. So this bond, these 2 bonds, and this bond, it doesn't get to keep any of them. But since it has the same electronegativity as the other sulfur, we can just split this one down the middle. It gets to keep that one and that one. So it actually has 2. So its oxidation number is +4. What about sulfur number 2? It's supposed to have 6. How many does it actually have?
6.
It actually has 6 as well. So its oxidation number is 0. So you add them. Wait a minute. Is that right? Yes. Yeah, so you add them all up. So oxygen 1 and 2, each are -2. So that's -4. The next oxygen also -2. This sulfur is +4, and that sulfur is 0. We add them all together, -2. So you should get the same charge, regardless if you add the oxidation numbers or you add the formal charges. You should get the same number. Oh, one other thing I want to point out when you're doing these is when you get to, I think the next one is, yeah, when you get to chlorine. Chlorine, 3, 4, 6. There's chlorine. So what's going to be the oxidation number of the chlorines? They should have 7
0.
electrons, and they both have 7. Yeah. And that's what you'll find, is that the oxidation number of an element in its most stable form will be 0. So O2, N2, H2, Cl2, F2, I2, they're all 0 until you react them with another element, and then they change. They'll either go down, they'll get more positive, that means they've been oxidized, or they'll get more negative, and that means they'll be reduced. So we'll talk about that when we talk about oxidation reduction reactions. So it's important to learn this now, so when we talk about oxidation reductions later, it won't be a whole completely different thing.
Excuse me.
Mm-hmm. Yes.
Can we have the configuration of nitrogen dioxide like this? Make a radical on the oxygen instead of
No, because then that gives the oxygen too many electrons.
Okay.
Because remember, neither nitrogen or oxygen can have more than 8 electrons. So that gives oxygen too many. That gives oxygen
mean,
9. That gives oxygen 9 electrons. It can only have 8.
I mean the this let me erase this. So one of the oxygen has has 2 lone pairs and 1 radical, and the other one has 3 pairs. Oh, okay.
Yeah, they can't have more than 8 electrons. That just can't be done.
Okay.
Yeah, so the only place you can put that is in the middle.
Professor,
Yeah.
for the one that we just did see, why can't we put all double bonds around sulfur? Or is that just how?
Oh, where are we? Oh, S2O3, the thiosulfate.
Yeah.
Okay, let's try that. So just do it like this.
Correct.
Okay, so how many? It was 32
Yes.
electrons. So that leaves us with 20. And so we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We need 4 more. Like that.
Because I was just thinking because S is
4.
below in the third period. I was just wondering.
Oh, wait, I think I know I added up the numbers wrong. Sorry. So 2, 4, 6, 8, 10, 12, 14. Oh, 16. That leaves us with 16. Oh, so just leave it like this.
Yeah. Is that possible?
Yes, but the problem with this one is that gives the negative charge so that gives the sulfur in the middle 8 electrons, right? So that gives the sulfur in the middle a -2 charge. And oxygen is more electronegative than sulfur. And so what'll happen is that oxygen is going to steal those electrons from the middle because it's more electronegative, and they'll just go back.
Okay. Okay. I understand. Okay.
Yeah. So yeah, it's theoretically it's possible, but it ain't going to happen because because oxygen's going to take those. If there's a negative charge and oxygen's around, that's where it's going. So yeah. No, but that's good to think about these things. Yeah, that could be made, but it's not going to. As remember, one of the rules for drawing these structures is that if there's going to be a charge, if it's going to be a negative charge, it's going to be on the more electronegative element. If there's going to be a positive charge, it's going to be on the less electronegative element. And the only thing that immediately comes to mind that doesn't work for is carbon monoxide. Because remember, with carbon monoxide, we basically wound up with a negative charge on the carbon and a positive charge on the oxygen, because basically that's the only way we can make it work. And so that's basically the structure it takes. But then the oxygen pulls this pair of electrons close to it. And so it makes it less and less and less polar, because that oxygen is pulling that negative charge so much toward itself that it basically turns it into a relatively nonpolar molecule. That's why it's a gas and not a liquid or an ionic substance. All right, so we have any other questions before we call it a day? Remember, we can talk more about this. I'm going to go over this again on Thursday, and we'll definitely talk about it. If you want to come to group meeting. I keep saying that. Keep thinking I'm still in research. Go to office hours tomorrow, or basically anytime you'd like, just drop me a line. We'll talk about it some more. Okay?
All right. Thank you, Professor.
Keep your fingers crossed tonight. I'm not sure if I'm hoping for a quick end to it or whether it'll go on for a month. I'm not sure. Either one would be amusing.
I think people are saying it's going to go on for at least like a week or so.
I know. I remember I was in Pasadena working when when Bush Gore happened. I was working at how was I working? No, I was working at the hospital at USC. And I went back to the hotel, and after dinner, I went, I was watching the returns, stayed up till about 2, and went to sleep, and woke up the next morning, still nothing. Like that never happened before. But
I don't think anybody will bow out this time either. I think they'll let the counting finish out all the way.
I know. Anyway, good luck, everyone.
Thank you, Professor. See you later.
All right, thank you, guys. We'll talk to you soon.
Professor?
Yeah.
How the oxidation number on each oxygen on ozone?
Okay. Where is my share? Oh, here it is. All right, so so we've got 18, 16, 14 electrons. So 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 14. So then got a double here, and I think then that's it, right? I think then we're sort of, that's the final structure. That's the final structure, right? Because we have a positive charge here and a negative charge there. So, so for as far as oxidation goes, since they're all oxygens, they get to keep they get to split all the shared electrons. So the oxidation number in this one would be 6 minus 6 equals 0. 1, 2, 3, 4, 5. The oxidation number would be +1. And over here would be -1. The same as the charge, because they're all oxygens. So when two atoms have the same electronegativity, you just split the electrons up.
Okay.
Yep.
And it would be polar downward, right?
Ozone. Well, because this isn't the final structure. Basically, it's a resonance structure. So the resonance structure is 1, 2, 3. Like this. It would be slightly polar because of the shape. But yeah, it's not really that polar molecule.
Okay.